Today we shall discuss algebraic numbers and algebraic integers. And before that we will study some properties of polynomials with rational coefficients. Polynomials with rational coefficients have many properties similar to integers. Like for integers, we have division algorithm. That is, if you take an integer m and n is a non-zero integer, then we can divide m by n, get a quotient and get a remainder. So m is equal to n times q plus r, where the remainder r is an integer such that 0 less than equal to r less than mod of n. If n is negative, you take mod of n, and the remainder is less than mod of n. So this is the division algorithm for integers. Similarly, we have division algorithm for polynomials with rational coefficients, or more generally polynomials over any field. So let fx belong to qx. This is the set of all polynomials in one variable x with coefficients from the field q of rational numbers. Let gx be a non-constant polynomial in Qx. Then there are polynomials Qx and Rx in Qx such that fx equal to gx qx plus rx, where rx equal to 0 or degree of rx is less than degree of gx. Here we can even take non-zero polynomial and we can divide by that. So let me say it is non-zero polynomial. If it is a constant polynomial, then Rx will be 0 only. So take Gx to be a non-zero polynomial. You are dividing fx by Gx, getting a quotient and getting a remainder. Qx and Rx are uniquely determined. This is the division algorithm, which is similar to the corresponding division algorithm for integers. So this is the division algorithm for polynomials. We will next see the GCD of two polynomials. So given two polynomials fx and gx belonging to qx, not both 0, there is a polynomial hx in qx such that hx divides fx, hx divides gx, and such that for any polynomial h1x that divides both fx and gx, we have that h1x divides hx. Hx is uniquely determined if we take it to be monic. That is, monic means leading coefficient is 1. Hx is called the GCD greatest common divisor of fx and gx. There exist polynomials capital Fx and capital Gx such that Hx is equal to Fx into capital Fx plus Gx into capital Gx. The GCD is a combination of the given polynomials. So, these polynomials can be obtained by Euclid's algorithm. The GCD of two polynomials in Qx can be written as their linear combination with So the GCD of two polynomials in Qx can be written as their linear combination with polynomial coefficients using Euclid's algorithm. Euclid's algorithm is you just divide fx by gx, get the quotient, get the remainder. Then by the remainder you again divide gx, get the quotient, get the remainder, and so on. Proceed like this. And the last non-zero remainder in this process is going to be the GCD of the polynomials, and it can be written by retracing the steps as the combination of the given polynomials. Now we define an irreducible polynomial. All polynomials we are considering are rational polynomials. So let fx in qx be a non-zero polynomial we say that fx is an irreducible polynomial if fx cannot be written as f1x into f2x with f1x, f2x in qx of positive degree. In fact, we take non-constant polynomial, that is fx in qx be a non-constant polynomial. We say that fx is an irreducible polynomial if fx cannot be written as f1x into f2x with f1, f2 of positive degree. Standard examples are that a linear polynomial is irreducible. If you take this polynomial x square plus 1 is irreducible, that is because if it is reducible, then x square plus 1 equal to f1x into f2x. Now degree of this is 2, therefore degree of both are of positive degree, and degree of f1x must be 1 and degree of f2x must also be 1. Both are degree 1 polynomials. There may be some leading coefficient and we can absorb the leading coefficient of one into the other and make both monic. So we may assume both monic. And then you will get x square plus 1 equal to x minus alpha into x minus beta. We can write x square plus 1 in this form, and that would mean that if you put x equal to alpha, right hand side is 0, this is 0. So these alpha and beta, they are rational numbers. These are polynomials over Q, so alpha beta are rational. Therefore, there exists alpha in Q such that alpha square plus 1 equal to 0, and that's a contradiction. Because alpha square is bigger equal 0, so this is bigger equal 1. property of an irreducible polynomial is if Px in Qx is an irreducible polynomial and Px divides product Fx into Gx, then either Px divides Fx or Px divides Gx. This is the property of an irreducible polynomial. It is the property of a prime number. So it is called as a prime polynomial sometimes. We also have every non-constant polynomial in Qx can be written as a product of irreducible polynomials. The product is unique this is called factorization. So you can say the factorization of a non-constant polynomial is unique apart from multiples by non-zero rationals and the order in which the factors are written. This property is described by saying that Qx, the set of polynomials over Q in one variable x, this is a ring, is a unique factorization domain. In short, we write UFD. Qx is a unique factorization domain. We define a primitive polynomial. A polynomial a naught x raised to n plus a1 x raised to n minus 1 plus etc. plus an ai belonging to z. All these coefficients are integers, and this is a non-zero polynomial we are taking. So these are in z not all zero. Is called a primitive polynomial if the GCD a naught, a1, etc. up to an is 1. So if some prime divides all ai, then that is not a primitive polynomial. So GCD of all the coefficients is required to be 1. Like 2x plus 3, this is a primitive polynomial, whereas if I take this is not a primitive polynomial, this is a primitive polynomials. And there is a result about primitive polynomials. Take two polynomials fx and gx which are primitive and take their product. The product will also be a primitive polynomial. That's the result. So the product of two primitive polynomials is primitive. This was the result obtained by Gauss, and a consequence of this obtained by Gauss is that suppose we have monic polynomial with integer coefficients. So if fx is a monic polynomial with integer coefficients, and fx equal to gx into hx with gx hx belonging to qx, both monic. Then gx and hx have integer coefficients. So this is a consequence of the result that product of two primitive polynomials is primitive. So take a polynomial with integer coefficients, factorize suppose you are able to write it as gx into hx, these are monic with rational coefficients, then the coefficients of gx and hx must be integers. Okay, now we define an algebraic integer and an algebraic number. So let alpha belong to C, complex numbers. C is the field of complex numbers. Alpha is said to be an algebraic number if alpha satisfies a non-zero polynomial equation with rational coefficients or equivalently with integer coefficients. Alpha satisfies a non-zero polynomial equation with rational coefficients or equivalently with integer coefficients. Like if you have some equation like 3/4 x square plus x plus 5/2 equal to 0 and some alpha satisfies this equation. This is a polynomial which is a rational polynomial of which alpha is a root. But then you can multiply by 4 throughout and we get 3x square plus 4x plus 10 equal to 0. This is a polynomial equation in which the coefficients are all integers. So alpha satisfies a non-zero polynomial equation with rational coefficients. We can replace rational by integer. Now we define an algebraic integer alpha in C is called an algebraic integer if there is a monic polynomial fx in Zx such that f of alpha equal to 0. F of alpha equal to 0. So alpha is a root of a monic polynomial with integer coefficients. So example, if you take root 2, it satisfies x square minus 2 equal to 0 and this is a monic polynomial and so root 2 is an algebraic integer. clearly an algebraic integer is an algebraic number if you have an algebraic integer, it satisfies some monic polynomial with integer coefficients, and the same polynomial can be used. Here we have seen algebraic number means alpha should satisfy some non-zero polynomial equation with rational coefficients. So because it is monic, it is a non-zero polynomial equation. Whereas you can find out algebraic numbers which are not algebraic integers. And simplest example is that take rational numbers like 2 by 3, rational numbers which are not integers, then they are algebraic integers, and they are not algebraic integers like 2 by 3 etc. This is not algebraic integer, but it is an algebraic number. So every rational number is an algebraic number. Every rational number is an algebraic number. Why? Because if alpha is rational, then alpha will satisfy x minus alpha equal to 0. If alpha is rational, x minus alpha, this polynomial is in Qx and alpha satisfies it. So alpha is an algebraic number. Algebraic number. We have the next proposition. If alpha is a rational number such that alpha is also an algebraic integer, then alpha is an integer. Alpha is an integer. To prove this, write alpha equal to A upon B with GCD of AB equal to 1. So A and B are integers and their GCD is 1. Suppose it is an algebraic integer, suppose alpha is an algebraic integer, that would mean that there is a monic polynomial with integer coefficients which is satisfied by alpha. Therefore, there is a monic polynomial fx equal to x raised to n plus a1 x raised to n minus 1 plus etc. plus an with ai belonging to z 1 less than equal to I less than equal to n, such that f of alpha equal to 0. Now alpha is a upon b, so substitute x equal to a upon b here, we should get 0. Therefore, a upon b raised to n plus a1 a upon b raised to n minus 1 plus and so on plus a upon b a n minus 1 plus a n equal to 0. Now multiply by b raised to n, multiply throughout by b raised to n. That gives us a raised to n plus a1 a raised to n minus 1 into b plus and so on, plus a, here we have a and we are multiplying by b raised to n, so a n minus 1 is there, a n minus 1 and b raised to n minus 1 plus a n b raised to n equal to 0. Now, we can take b to be positive and suppose if possible some prime p divides b. If p is a prime, that divides b, see that p divides this term and all the later terms. We see that p divides a raised to n, and if p divides a raised to n, p is a prime number, so p has to divide a, so p divides a. And this is a contradiction because we have already assumed that GCD of A and B is 1. As AB equal to 1. Therefore, no prime can divide B, and therefore B has to be plus or minus 1. If you assume it to be positive, then it is plus 1. And therefore, alpha equal to A upon B, that has to be in Z. and that shows that if an algebraic integer is in Q, it's a rational number, then it must be an integer. So this shows that an algebraic integer in Q must be in Z. And immediately you get examples, as I mentioned, that 2 by 3 is not an algebraic integer. Although it is an algebraic number. Algebraic number. There are plenty of real numbers which are not algebraic numbers. This can be shown using cardinality arguments. So, note if an equal to the set of polynomials of degree n with rational coefficients, then an is a countable set. Polynomials of degree n. So, such a polynomial is of the form a naught x raised to n plus etc. plus an. This is not equal to 0 if you want degree to be exactly n, and these are all non-zero elements of Q, rational numbers. But you know that this is a countable set. So Q is countable, this is non-zero elements of Q that is countable, and so this is, if you take the n plus 1 tuples, a0, a1, etc., an, then these n plus 1 tuples form a countable set, and every n plus 1 tuple corresponds to a polynomial. So the set of all polynomials of degree n with rational coefficients is a countable set. Now, if you take any such polynomial, it will have at most n roots. Any such polynomial has at most n complex roots or zeros. So if you take Bn equal to the set of zeros of all polynomials of degree n is a countable set. Set of zeros of polynomials of degree n, that's a countable set. And if you take any algebraic number, then it is in one of these Bn. So, the set of all algebraic numbers is union of Bn n equal to 1 to infinity. Each Bn being countable, this is a countable set. As each Bn is countable. Since R and C are both uncountable, there are uncountably many complex numbers and also uncountably many real numbers. Which are not algebraic numbers, which are not such numbers are called transcendental numbers. A complex number which is not an algebraic number is called a transcendental number. A complex number which is not an algebraic number is called a transcendental number. So the previous discussion shows that there are uncountably many transcendental numbers which are real or complex. Thus, there are many transcendental numbers. It is difficult to construct examples of transcendental numbers. Some known numbers which are not algebraic are E, pi, these are transcendental numbers. You can consider the values of the zeta function like zeta of 2 equal to 1 upon 1 square plus 1 upon 2 square plus etc. This sum of this series is pi square upon 6. This is a transcendental number. If you consider zeta of 2n, it is transcendental. If you take one transcendental number, its powers are also transcendental. Like pi square, pi raised to 4, pi raised to 100, they are all transcendental numbers. You can prove that very easily that, see, suppose alpha is, so note, from a known transcendental number, then alpha raised to n, n bigger or equal 1, is also transcendental. You can construct such transcendental numbers very easily. Or in general, you should take f of alpha, where fx belongs to qx, degree of fx bigger or equal 1, that is a non-constant polynomial. Then you take f of alpha, this is also transcendental. That is because if this is an algebraic number, then it will satisfy some polynomial with rational coefficients. And from that you get a polynomial for alpha also with rational coefficients. That's a contradiction because alpha is transcendental. So from one transcendental number you can construct plenty of transcendental numbers like this. We will see more about algebraic numbers in later lectures.